Okay, so we're going to be doing mechanisms here, and the first mechanism I want to do is acid-base mechanism, proton. I also call this proton transfer. And other people, I guess, call that proton transfer. You may want to get your textbook out if you're not using Paula, the organic chemistry text by Paula Bruce, then you have to find it. But if you're using Bruce, 7th edition, then it's section 2.3, page 59. And this is where the mechanism is. And I just want to walk you through it. I realize that, in a sense, I'm just reading the book here to you. But here's how this works. By definition, I'm going to do general first, and then I'm going to go with some specific examples. By general definition, we oftentimes use an acid as something that's got a proton that it can donate, right? We're dealing with Bronsted-Lowry acid-base definitions. This is the most common one, and so I want to spend the most time with this one. Here's an acid, and we use A, sort of, I guess, because it's an acid. And we use A for acid, right? And we use B for base. So I'm going to use B for base like that. An acid plus a base. In the simplest terms, let's say it's going to be bidirectional, and you'll see why in a second. These electrons attack that proton, and these electrons then are pushed off. Okay? And so if that's the case, what are the products of this reaction? Those are electrons right there, of course, right? It's a bond. They were covalent. Now they're a lone pair. And there's going to be a minus on there, right? Because it was neutral before. Okay, when a bond goes to a lone pair, then the charge goes down by 1. All right? And when a lone pair goes to a bond, the charge goes up by 1. Right? And that's why that's the answer for that, okay? So this is really an equilibrium. And I'd say we can use equilibrium no matter what the ratio of these. Oftentimes we learn in Gen Chem that we have reactions which we call irreversible. And they're not technically irreversible. It just turns out that the products vastly dominate. And if the products vastly dominate, in other words, if the back reaction is negligible, then we might say it's irreversible. So that's the first mechanism. All right, let's do an example now with, I think, the one that's on page 59. Yeah, it's methanol and hydroxide. All right, methanol. Actually, I'm going to do one simpler than that. I'm going to do HCl plus water. Okay, I'm drawing it like that because I want the lone pair of electrons to be on this side, so we can sort of do a parallelism here with that. And I want the hydrogen to be on this side. This is just HCl, right? It's just someone looking from the other side of HCl. Lone pairs of electrons here. All right, and so the mechanism for this is what? All right, so we think of HCl as a strong acid. This is very much of a strong tendency to donate its proton. You'd be tempted to draw the arrow maybe from the proton, but that's not the way mechanisms go. With our curved arrow notation, we always draw the arrow as the action of the electrons. Again, there's comments about this on page 59 in the Bruce text, section 2.3. And no matter what text you've got, there'll be comments about curved arrow notation. Sometimes they're called curly arrows, I think. All right. So if those go to attack that proton, hydrogen can only handle one bond at a time. So those electrons are going to get pushed off. Can you see the parallelism between these two? Okay. So this then goes to, I should have given you a second to predict what it goes to. All right. So just redrawing this. Oops, I drew the bond here. Obviously that doesn't matter, right? Is that clear to you that those two lone pairs of electrons are equivalent? Okay. And of course we draw that as an equilibrium. All right, so you learned in Gen Chem that this was a strong acid, which means that the back reaction is negligible. We almost always draw that as a forward as an irreversible reaction, which is a single arrow going forward. Let's talk about how we can evaluate which direction these go. Actually, no. Let's do that in a different video. For now, let's just focus on the mechanism itself. Okay. So that's one version of it. Let's do another one. Let's do the one that's on page CH3OH is on page 59. H2O. I'm going to draw it a little bit different this time. Give you a chance to do some practice. All right, pause. Maybe you should pause the video here at this point and see if you can predict what's going to happen with a closed book. Okay, so let's suppose you just paused it and restarted it, and the electrons are going to go here to the hydrogen, which is ionizable, and that's going to go there. This is going to give us CH3 plus H3O plus. Okay. Now, notice, by the way, I drew the bond out here. I did not draw the bond out here. It's still there. I just didn't draw it out. There's also bonds, of course, right between these hydrogens and carbons, or hydrogens and that carbon. Okay, let's do one more. Let's do acetic acid. CH3 COOH plus water. In a separate video, I'll talk about, I'm going to use these exact same three reactions for something else. All right, to illustrate something else that we need to know about acids and bases. But this one's just strictly for the mechanism. Okay, look, you might want to pause it here and then make a guess about what's going to happen. Okay, so let's suppose you paused it. You've unpaused it now, and these electrons go here, and these electrons go here. And that gives us that. Okay? And that's the answer. Okay, so there's an introduction to mechanisms of acid-base or proton transfer.